Okay, let's take a look at an exercise now that involves impulse. So remember here that impulse, this is, there's a J to symbolize it, and this is a change in momentum, which is also equal to a force applied over some time interval. So depending on what sort of information we have readily available or given to us in the exercise, we can use different things in order to find impulse. So, but fundamentally, it's dealing with momentum, right? So maybe we'll start out with a before and after picture. So we have this ball, kind of like before being hit. Here's the ball, right here. And then after being hit, immediately after the collision, it's over here. Well, separate picture. It's over here, and initially it had some velocity equal to 0. Now it has some other velocity equal to not 0, right? And then there's actually a third one, kind of like a long time after. We'll call it long after. And it's up over here. And we can then, if we establish a datum across here, so there's some datum here. This is where my height is equal to 0. Then it travels up to a maximum height of 5.5 meters, right? So, and then it comes to rest, and then the velocity is actually 0 up here when it's at the top as well. So what we can do, thinking about, impulse is a change in momentum. Since it started out at rest over here, the initial momentum was equal to 0 as well, right? And so if I can find out, basically what the momentum was after it was hit, then that would be the change in momentum, right? Because the initial momentum was 0. So all we really need to do is find out the momentum after it's being hit. That would be our change in momentum, which is by definition impulse. So we have the mass of it, 57 grams. And so all we really need is just this speed after it's hit. Well, they tell us that it goes 5.5 meters up, so we can actually, find out what speed it was traveling when it was down here, just based on, conservation of energy, right? And so taking, maybe this is like 0.1, 0.2, and 0.3 over here. So using conservation of energy from 2 to 3, so 2 to 3, we'll use conservation of mechanical energy, and what we end up with here is that 1/2 mv2 squared is equal to mgh, right? This would be we only have kinetic at 0.2 and only have gravitational potential at 0.3, and we have the h there, right? And so we can find out that v2, these masses cancel out, right? And so v2 is the square root of 2gh, or the square root of 2 times 9.8 times 5.5. Right, so we have the speed at 2 is equal to 10.38 meters per second. So in order for this ball to travel up this high, assuming air resistance like we usually do, then it had to be moving at 10.38 meters per second immediately after the impulse. And I'm assuming, obviously, that the ball didn't move between the racket initially hitting it and then the racket kind of being moved away. So, because we assume this impulse is instantaneous, which we actually call an impulsive force if it's instantaneous. So V2 is this, and then so we can find out what the momentum is at 2 then. So then the momentum in state 2 is just going to be mass times V2, right? And so this is the 57 grams times 10.38 meters per second. And the momentum at 2 is 0.59 kilogram meters per second. But just as we said, since the momentum at 1 equals 0, then we have the change momentum is just going to be equal to the momentum at 2. So that's the 0.59 kilogram meters per second. And yeah, that's impulse. I guess if we were to expand this, if we had like a time interval, say that this occurred over actually 1 millisecond or something like that, then we could find out from that, we could say this is force over time. If I gave a very, very small time interval, it doesn't actually happen over a time of 0, but let's say this is 1 millisecond. That's 1 times 10 to the negative 6th seconds, very, very small amount. Then we could actually find out what the average force would be applied to this, which would be very, very large, right? It'd be 590,000 newtons. It's a lot.